So in this problem, we have, it's kind of a biophysics problem. We have ourselves a neuron. And mind you, I don't even know what a neuron looks like. I just, for some reason, have this visualization and looks like a very long bone, which I don't think it does. And between two neurons, there's a section of space called the synapses. And what ends up happening in the case of, let's say you stub your toe. So let's say that this neuron is attached to your toes, goes up your leg to your spinal column, and then a little section here jumps across the synapses, and then this section of the neuron goes all the way up to the brain. Okay? Now obviously it's not directly hardwired into the brain. It's once again a synapses here. Okay? And then in these synapses, when this end of the neuron is stimulated, it releases a neurotransmitter, okay, which then carries the signal to the next synapses, or to the next neuron, sorry. So in this problem, we're claiming that the neuron is 1.0 meters in length. Okay, so each one of these neurons is exactly 1.0 meters in length. The other thing that we're claiming is that the signal from this end to this end travels at a speed of 100 meters per second. Okay? Also, in the synapses, the section where the neurotransmitters are being released, we know that the distance is approximately 100 nanometers. Oh, look at that. Nanometers. Well, let me make that a little bigger. The problem is 100 nanometers. And it takes 0.10 milliseconds to travel that, milliseconds, not meters per second. It's ingrained in my brain. Seeing MS together, I think meters per second. Okay? So the first part of the question is it's asking you what the average speed is across this region from here to here. Well, speed, unlike velocity, speed is distance divided by time. If you remember, velocity is displacement divided by time. Speed is distance divided by time. Two different ideas. Okay? In this case, our distance is going to be 100 nanometers, and our time 0.10 milliseconds. Okay? Cool? Well, the next thing I'm going to do is I'm going to express this differently. I don't want it in nanometers per millisecond. I want it in meters per second. So that's going to be 100 times 10 to the negative 9 meters. That's the conversion from nanometers to meters. This is 10 to the negative 9. Then I have my time, 0.01 times 10 to the negative 3 seconds. So there's a conversion from milliseconds to seconds. Okay? Now, when dealing with exponents, when powers of 10 are in play, if they're multiplied together, we add the exponents together. If they're divided by each other, in this case they're divided by each other, we take this one, the top one, and subtract the bottom one from that value. Okay? So, to do that, all we do is I'm going to separate this term, 100 over 0.1 meters per second, I'm just going to move those units out to the front, times 10 to the power of negative 9 over 10 to the negative 3. I subtract these, so I'm left with negative 9 minus a negative 3. Well, that turns into a negative 9 plus 3, giving me negative 6. Okay? So that means I have 100 meters per 0.1 seconds times 10 to the negative 6. Okay, not moving very, very fast. Now, what I also can do is I can do this little trick. This situation right here, 100 meters in 0.1 seconds, translates, so move that over one place, which means I have to move the decimal place over one place in the top, and I'm left with 1,000 meters per second times 10 to the negative 6. Not all that user-friendly. There's still one more thing I can do. I'm running out of space over here, so I'm going to do it over here. So I'm left with 10,000 meters per second times 10 to the negative 6. This is actually 1.0 times 10 to the 1, 2, 3 third power times 10 to the negative 6. So in this case, I subtracted when they're divided. In this case, I have multiplication. So I'm going to add them together. Well, that's going to be 1.0 meters per second and 3 minus 6, or because it would be 3 plus a negative 6. This is my 3 plus negative 6. I'm left with negative 3. So that's going to be times 10 to the negative third, or my final answer, which I'm going to clear some space for, 1.0 times 10 to the negative third meters per second. A very, very slow moving bit of information, which makes sense because actually what's going on there, chemicals are being released in a fluid and using a potential, basically what we'll find out later, a voltage. They're stimulated to move across that distance, but it's a fluid there, so it's got to move. You got to let the fluid diffuse over there. Okay, cool. So that was part A. I'm going to write it under the information I have. Erase this part. Okay, so that was 1.0 times 10 to the negative 3 meters per second as the speed across the synapses. Now, part B, we're trying to figure out how long it takes for a signal to reach the brain. Well, I already have two sections of time already spelled out to me. This one and this one. Both of those are going to be this 0.10 milliseconds. So I'm just going to write it down here as 0.10 milliseconds plus the time for that synapses. Well, let's put an addition sign in there. Plus the time to travel across that neuron, plus 0.0 milliseconds. And then I have this neuron over here. So what I've got to do is I've got to figure out time from this. Well, I know speed. Write it up here. Speed is distance divided by time. I need to solve for time. Okay, so what I'm going to do is I'm going to move the time over to this and move the speed over to that using cross multiplication. So I'm left with time is equal to distance, in this case 1.0 meters, divided by its speed, 100 meters per second. Okay? The meters cancel out. I can see that right away. Then I'm left with a second. Cool? Now, what's 1 divided by 100? Well, I can do this one of two ways. I can use my brain and just kind of do it mathematically, or I can take it in steps. So I have t 1.0 times 10 to the 1 divided by 1.0 times 10 to the 2, and I'm left with, because it's a subtraction, to the negative 1. Or I could have done it this way. 1, 2, 1, 2. I end up with 0.01. Oh, wait a minute. That would be not, that's to the 0. That's why it makes sense. Then I'd have 0 minus 2 and then move it over. Yeah. Okay. 0.01 seconds plus this in milliseconds plus 0.01 seconds. Once I solve for this one, I've automatically solved for this one. because the math doesn't change, plus this last neuron, which is 0.1 milliseconds. Why do I keep doing that, McNeil? Milliseconds. Okay? Well, I got them seconds and milliseconds. I'd rather have them in seconds because that's our base unit. So 0.01 seconds plus milli, 10 to the negative 3. That means this decimal place is going to move this way 3 places. So 1, 2, 3. 0.00010 seconds plus 0.01 seconds plus 0.00010 seconds. Add them together, I get 0.02 seconds for the neurons, and then for the synapses, plus 0.0002 seconds. Add these together, I get 0.0202 seconds. Okay? So that is the amount of time it takes for a signal to start from your toe and reach your brain. Okay? Cool? So there's the second part of that, the amount of time that it takes. The last part is, what is the average speed of propagation? How fast does my speed travel? Or does that signal travel? Well, this is going to be an important piece of information, so I'm going to leave it right where it is. Okay? I'm going to erase everything else. Except for I needed to keep the 100 nanometers. Okay? So, the speed is going to be equal to distance divided by time. I have my time already. All I need to do is figure out my distance. Well, it's going to be 1.0 plus 1.0, the neurons, plus this. Remember, that's 10 to the negative 6. So what I'm going to do is I'm going to move that decimal place over. 1, 2, 3, 10 to the negative 3. 1, 2, 3. Oops, sorry, it's not 10 to the negative 6, it's 10 to the negative 9, isn't it? 1, 2, 3. So there's 9 places. So you end up with 0.000001 plus I got one. 0.00001 meters. Okay, it's basically 2 meters. I mean, I can put those in there, but it serves really no purpose. So 2.0 1, 2, 3, 4, 5 1, 2, 3, 4, 5 2 meters divided by 0.202 seconds. That's the average speed. I'm not going to do the calculations. I don't have my calculator with me, but that's how I would calculate the average speed for the entire system. Okay? You'll find it to be approximately the same as the speed as of which it travels across the neurons.